press that little button until the green light comes on. And then Nick, can you grab it?
Here we go, 10 seconds.
Grab the sheet.
That
Okay.
sheet. He'll give you the DVD.
Okay.
Good luck.
Thank you.
3, 2, 1.
Good afternoon. Welcome to CERIAS Security Seminar. Today it's my pleasure to introduce Omar Chowdhury. He's currently a postdoc in my group. Before joining Purdue, he was a postdoc at CMU. And before that, he received his PhD in computer science from University of Texas in San Antonio, working under the supervision of the late Professor Will Winsborough, who was a very good friend with me, and we collaborated on many papers before. And Omar worked on a large range of areas. Today, he will talk about regulatory compliance.
Okay, thank you for the introduction, Minghui. So, hello everybody. So, I'm going to talk a little bit about regulatory compliance checking over encrypted audit logs. And this is a joint work with my colleague at Carnegie Mellon University, Anupam Datta Liminjia, and my another colleague from Max Planck Institute of Software Systems, Deepak Garg. Okay, so before I start talking about what I'm going to talk today, I want to put a little bit of disclaimer. So when I use the word regulatory compliance, I use it in a kind of more relaxed fashion. So regulatory compliance, at least in the U.S. federal judiciary system, is the final say is by the judge. So a lawyer or a normal guy like me do not know what the interpretation of the law should be. So take this work with a grain of salt. So, and the other thing is, this is our interpretation of the regulation. And we have actually verified with a lot of other computer scientists interpretation of the regulation, and they tend to match up. Okay, so that being said, so I'm going to talk about actually privacy regulations per se. Now, we have human users of internet, right? We share our information with a lot of organizations, and they in turn give us some services. So example organizations are like hospitals, your university, banks, or even Google, right? And let's take one representative organization, say hospital. Now, assume Homer Simpson goes to the hospital for treatment, right? And he gives his personal information, like date of birth, name, social security, blood group, so on and so forth, and medical records. Now, during treatment, right, the hospital can send this information to a lot of other parties. For instance, the Homer Simpson needs an X-ray, so all these medical records have to be sent to the lab. Now, Homer Simpson needs to be billed for that visit, so all the records should be sent to the health insurance so that they can verify whether the visit and the test they have done is legitimate and whether they were necessary. And finally, for medication, they should be sent to the pharmacy so that they can figure out drug interaction and so on and so forth. Now the obvious question is, what is stopping the hospital from selling it in a black market? So our medical records go price for a black market is $32, right? So it's not very small, right? And there is a lot of patients in the hospital. If they sell all of them, they can make a lot of money. But thank God, government has stepped in. So they have a privacy regulation, which they call HIPAA. It stands for Health Insurance Portability and Accountability Act. So all these interactions are under HIPAA. Like, it's regulated by HIPAA. So HIPAA basically regulates how healthcare organizations can share the collected personal information from the patients. That's basically what it mandates. Now, as you have figured out, the first three, according to HIPAA, are allowed because they're for treatment and billing and operations, and the last one is not allowed. Okay, so we're good. Now the question is, what if we violate HIPAA? An organization violates HIPAA. Now, like any regulation, violating HIPAA has serious implications. You can be prosecuted. You could pay a lot of fine. Okay. Now, I'll show you two example scenarios, right, where organization or an individual violated HIPAA. and they were penalized with civil money penalties. Now the thing to look out for is the staggering amount of fines, right? It's in one case it's $4.3 million, other is $1.44 million. So violating HIPAA can have serious implications for your reputation or even financially. Actually, in the HHS website, they have a wall of shame. It basically captures all the violating organization where they violated like more than 500 times of a HIPAA regulation. So it's bad for your reputation too. Now, to circumvent this situation, what does the organizations do? They generally capture all the privacy sensitive events in paper trail, right? And they bring in an auditor periodically. It depends on the organization, and who actually goes through these records and analyzes the privacy policy to make a judgment call whether something is a violation or not, right? Now, as you might have imagined, this is largely a manual effort. So, and the privacy laws can be huge, like HIPAA is like 100 pages, right? And as this is a human effort, it could be error prone. Like you could miss a violation, or you could report something as violation, and it's time consuming. Like generally 4 or 5 people comes in and does this audit. So my research agenda so far has been to improve this situation, like trying to make this automatic a little bit, at least, even not fully possible, a little bit. So one possibility is let go of the paper trail, put it on the database so that we can search. Now, what about this regulation? We change it to a logic. It basically so that a human can read it and analyze it. And finally, let go of the human auditor and put in an automatic compliance checker that would take this audit record, electronic disclosure records and the computer readable policy, and will tell you, okay, violation, not violation. Okay. So my existing work and my previous work has focused mainly on the policy analysis part and trying to improve the state of the art of the automatic compliance checker. So the current context is a little different. Okay. So let's say a hospital, right? And it has its disclosure records in a database. Now, these audit logs can be very large, like from gigabytes to terabytes. Now, and with the cost effectiveness of cloud, it's a viable option to actually put it in the cloud. Like use the cloud storage infrastructure for storing the audit logs, right? Now, but the thing is what if the cloud gets broken into? These things are in plain text. Then everybody can look through it, and it's bad actually. So one possibility, and the other thing is this audit records actually stores personal information or proprietary information of the organization. So you can't just put it on the cloud with plain text. So one possibility is encrypt them. Now, as you might have known that if you do semantically secure encryption, it does not leak any additional information. Now, if that is the case, how can we perform audit? It's not clear. I mean, the encrypted audit log does not leak any information. How can we perform audit? So one possibility is use fully homomorphic encryption. Now, but that's light years away from being practical. It has very, very high overhead. So what we propose at this work, ongoing work, is basically a specialized encryption schemes just for auditing. That's it. It doesn't give you any other functionality, just for auditing, and change an existing audit algorithm, very small amount, so that it can handle encrypted audit logs. Now, so what it basically takes, the algorithm is an encrypted audit log and a constant encrypted policy. I'll introduce what that is, and it responds yes and no, whether there are violations or there are no violations. Okay, so interesting research questions in this arena would be, what operations over encrypted data are required to perform audit? I mean, if we are to perform audit, we need some operation on the encrypted data. We can't just do nothing. And the other question is, what kind of security assurance we can give. I mean, can we give like any assurance? So I'll try to answer the first question with a couple of examples. Say, very simple example policy, which basically says every individual accessing sensitive patient information is in the role of a doctor. That's basically what the policy says, that anybody who's accessing the patient's information should be a doctor. It's unrealistic policy, but that is like for the sake of example. Say our log is something like this. Like you'd have a sensitive access table which will tell you who accessed sensitive information at what time, and the other relevant table would be a role table which basically tell which employee is in what role, right? Now, to check actually compliance, what we would need to do is basically go through the sensitive access table one row at a time and get that employee name and try to figure out what his role is. So it's basically taking a join of these two tables. So it's basically taking a join of these two database tables. So we would need join. That's what we figured out from the first example. The second example basically says, if a patient's medical record is accessed by a billing department employee, it means that a patient might have visited the facilities in past 1 month. That's basically what it says. And in this case, we'll have these say relevant tables in the audit log, which basically said one table would keep the patient visit situations where it says Alice visited at time T1, Eve visited at time T2, and the medical record access time, which basically says that Alice's record was accessed by John at time TJ. And there is this other relevant table, it says employee department table, which basically says John's department is billing. Okay. So what we have to do basically is go through one row at a time from the medical record access table, figure out what is Alice's visit time and what is the John's department, right? So what we do is like take two joins, right, of these three tables. Now say we got this row satisfies the condition of the join. Now what we want to additionally check is this 2 times difference is less than 31 days, right? So that's basically the additional information. We have to be able to compare 2 times. So to summarize, what operations we basically need are, okay, join operation, which is a specialized kind of equality checking, and time step comparison. It's basically checking that if you have an encrypted time and an encrypted time offset, it's less than equals to another encrypted time and another offset. So before I jump into the agenda, if anybody has any questions, I'll be more than happy to take it. It doesn't have to be at the end of the talk. It could be anything in the middle. So there is a lot of logic stuff in this work. So I would like, if anybody has any specific questions, feel free to stop me in the middle. Okay, so seems nobody has any questions so far. So for the agenda today's talk, so I'm first going to talk about what is our policy language, right? How would we represent the natural language policies? So we talked about a computer readable policy. So what that means? So what is the syntax and semantics of that? And talk about the 2 log encryption schemes we're going to introduce, and an enhanced auditing algorithm. It's basically enhanced for handling encrypted audit logs. So this audit, the main algorithm was for a plain text log. We tweaked a little bit, not too much, a little bit to handle encrypted audit log. Okay, and the next thing we are going to discuss is security guarantees. What guarantees can it give? And we're going to then talk about some experimental results. So we ran some experimental results to figure out what is the computational overhead over plain text version. I mean, if you were to run the algorithm on the encrypted log, what is the additional overhead we have to incur? And finally, we'll summarize. So our policy specification logic looks like this. Okay, so I know this is scary, but I'll run it through. I'll run through each of them. So the first is what we call atoms, and the next part is guard. These are building blocks. So the main policy's specification is on the formula part. That's how you represent policies. And the first two are building blocks that are necessary for this one. So atoms are either predicate or a table. So it's a predicate. So we looked at the sensitive access tables. These are table names, actually. You can view them as table names, right? Then we have this other predicate, which basically is checking for time, right? We wanted to check time. And there is then there is equality. You can check whether two things are equal. And the next section is guard. Guard is a specific kind of formula. We'll explain this in a bit. Okay, so let's look at the formula, which is basically how you represent your policies. It could be a table name. It could just be a table name, or it could be true or false, right? Or it could be a conjunction of two policies, or a disjunction of two policies, or you have quantified formula. So quantified formula, the first one, what you have to read is, for all x that satisfies G, also satisfy this phi. That's how it's read. The second formula basically reads, there exists x for which, if it satisfies G, it also satisfies phi. So the first one is called universal quantification. The second one is called existential quantification. So you can see the relation that universal basically says for all x, something has to be satisfied. For existential, it basically says there should be at least one instance for which the formula should be satisfied. Okay. Now let's look at some example policies. So we'll take an example policy from GLBA, which is the full form is Gramm-Leach-Bliley Act. It's for financial organizations. Okay. Say the regulation basically says is a financial organization can share a customer's non-public information. Non-public information means your account number, your social security number, your credit score, possibly, with a non-affiliate. If either a privacy notice has been sent to the customer within the last 30 days, or a privacy notice will be sent within the next 30 days of the disclosure. That's basically what the regulation says. Now let's look at the scary part. Okay, so this is how it's represented in the logic. Okay, so I'll try to go through each of them. It's not very difficult once I explain to you. So it basically says if P1 is sending P2 a message M at time T. So that's the first part, right? It's basically said P1 is sending P2 a message M at time T, and the message is tagged as Q's attribute T, A. Implies that P1 is an organization, financial organization. P2 is not an affiliate of P1 according to time T. Q is a customer, and the attribute is a non-public information, right? And the next part basically says a privacy notice has been sent within the last 30 days, or a privacy notice will be sent within the next 30 days, so in future. So that's basically what the regulation looks like in the logic. Okay, so hopefully that's the end of the logic part. You're not going to see a lot about this anymore. Okay, so our audit log encryption schemes there are two. So we call them Enumia, Det, and KH. So Enumia is the Greek goddess of laws and regulation for human society. So that's how the name came to life. So, right, so we're gonna talk, so each of them have, each of the encryption schemes have their relative advantage and disadvantages, okay? So now let's walk through them. The first one says, the deterministic one uses, Enumia Det uses deterministic encryption. So deterministic encryption is basically an encryption scheme that if you take the same key and the same message, you're gonna always generate the same ciphertext. It's for Enumia KH uses keyed hash. That's how the name keyed hash. So it's basically a hash function that additionally takes a key. The Enumia Det is less flexible. So encrypt the log for a fixed policy. After that, you can't change the policy. That's fixed. So it's less flexible. For KH, however, it's more flexible. Once you encrypt it, you can check any policy. It doesn't matter. Okay. For enumerated, you have less computational overhead over plain text. Whereas for KH, you have more overhead. Like it takes more time. Okay. And for the enumerated, the log size has moderate space overhead, not too much. Whereas the enumerated has huge space overhead. I'll tell you why. It's very simple. It's not rocket science actually. And the enumerated has less secure, right? And its security is proved on a random oracle model, and it's sometimes called the heuristical model. And for enumerated KH is more secure. The security is proved on the standard model. So as you can see, each of them has their trade-offs. If you want more efficiency, you'll go for enumerated. If you want more security, you'll go for enumerated KH. So it depends on your application scenario. There is no like last word that you have to choose this or that. It depends on your application scenario. Now let's look at how we would encrypt using enumerated. It's very, as I mentioned, this is very simple. I mean, there is no like rocket science in it. So let's say we have these two tables in the audit log, right? The sensitive access table and the role table. So basically what it says is every column would be deterministically encrypted with a different key, except we have two restrictions. The first restriction is any two columns that are going to be joined together, they're going to share the same key. That's one thing. That's how you check equality or take a join. And the time, any column that has time, you will encrypt it with a special key. It's called K time, right? It's a every time would be encrypted with the same key, K time. And all the other columns would be encrypted with any other key. So each can be encrypted with a unique key. Okay. So that's basically it. That's how you do it with enumerated, right? So as you have noticed, this actually enables you to check join. I did not mention about checking order of the time. So that's I'm going to leave it for a little bit later. It's a little tricky, but it's not very difficult. So enumerated KH is a special, uses a special keyed hash. So it's not like a traditional keyed hash you would see in your literature, right? So it has a special property. So I'm going to talk about it. So it's like any other keyed hash, is a deterministic encryption. It takes a value, it takes a key, it outputs a keyed hash value, right? That's basically what it does. Say you have two values, U and V, and they are taken keyed hash with respect to keys K1 and K2 respectively. And you would get like H1 and H2, right? Now, if the keys are equal, you can actually check equality of UV just by checking whether H1 equals to H2, right? That's basically it. But that's not the interesting case. The interesting case is the other case, where if K1 is not equal to K2. Then how can you check equality between two elements? So basically how this keyed hash works is anybody who has K1 and K2 access to the two keys can generate a token, delta K1 to K2, right? So what it basically allows you to do is like if you have keyed hash of U with K1 and this transfer key, you can actually generate the keyed hash of U with just K2, right? Then you can basically check whether it's equal to the keyed hash of VK2. That's basically it. So that's the special property. Now, so this is more simpler. This is basically for each of these columns, you would have a unique key. Every column of the of each table, unique key. You'll encrypt using unique key. But whenever you're going to take a joins between two columns, you're going to generate this transfer keys, right? This transfer key. So that lets you transfer from one column to to another. Now, we're going to talk a little bit about how we're going to encrypt each individual value, right? So say we are trying to encrypt the value V with key K, right? That's our goal. So the ciphertext would be a pair. The first part would be the keyed hash version with that key. And the second part is a probabilistic encryption. It could be any encryption, AES, whatever, as long as it's semantically secure, you can use it. So one value becomes a pair, right? Hence the high overhead, high space overhead we talked about, that KH has high space overhead, right? And additionally, these keyed hashes are longer than the normal plain text value. So that's how the overhead comes. And for encrypting timestamps, we have been talking about timestamps, right? And we're gonna somehow check their order because that's what's necessary for our policies. So what we're gonna do basically is go through the log, pick out all the unique timestamps, and encrypt it with the special key we talked about, K-time, right? And add it to the specific data structure. I'll talk about this data structure in a bit. So this data structure will let you, so if you take two encrypted timestamps, it will tell you what is the order of them, because that's basically what we need for our policy checking. So I have been talking about this constant encrypted policies, right? So I told you guys that I'm gonna introduce that. So let's see an example. So this is the example policy, right? So don't worry, I'm not gonna run it through it. If you see, there are actually constants in this policy, right? Now, so this institution, this NPI, that's 0, 30. Now, all my information in the log are encrypted, but I have here is plain text. So I can't actually check plain text with an encryption. I can't just search them like that. So what I do, this is just for functional reasons, is encrypt these constants too. So instead of giving this policy, I'll give this constant encrypted policy where these encryptions are constants are all encrypted. And the only difference is this time offset constants, where it appears in the time order, are encrypted with the K-time key. That's basically what we have so far. Okay. Questions? No questions so far? Okay, well and good. So now we're going to talk about this magical data structure that we have been talking about for comparing timestamps. Okay, so it's called MOPED data structure. Okay, so what are the functionalities? So the functionality is you can pick any two encrypted timestamps from the log and pick any two constants, distance constant offset from the policy, and what you basically want to check is the value of this time order, whether this thing holds. That is, T1 plus D1 is less than equal to T2 plus D2. Now, T1 and D1 are this plain text version of ET1 and ED1. It's basically the plain text value. Okay. So what you basically want to do is check this T1 plus D1 is less than equal to T2 plus D2. That's basically what you want to do. Now, so what we basically do is you take all the unique timestamps from the log and you take all the unique time offset constants. So you add T and T plus DI in the data structure. That's what you do. For all time, you do that. For all unique time, you do that. Once that is done, now we are ready to query. So the data structure looks something like this. It's not very difficult to understand what it does. Okay. So there are other supporting data structure, but these two data structures are very simple. So the first one basically says, so it says ET1 7. So ET1 is a encrypted time, right? And you can view this as a hash table, where the key is this encrypted timestamps. Now the value 7, what does that mean? So what it means is if you were to use, like, decrypt all these encrypted timestamps, right? You put it in an array and you sort them, right? Instead of these encrypted timestamps, you just take the plain text timestamps. You put it in an array, you sort them, right? For each time, it will have a position in the array, like say, like number 2, number 3, 7, something. And then what you do is like do a reverse map. Now you keep that ET1 is the encrypted time and 7 is the position of the plain text time. That's what you keep a map of. It's in a hash table. The next thing basically says is ET4, ED1. So these are the two keys, and the value is the ET3, D1. So what it basically means is, if you add this ET4 and ED1, you'll get a time ET3, D1. So because we don't, like, our encryption does not allow us to add. So we have to keep this mapping explicitly. There is no way we could calculate addition. Now, okay, so let's say we have a query, say ET1, ED1, ET2, ED2, and we want to know whether ET1 plus ED1 is less than equal to ET2 plus ED2. Now, the first thing we're going to do is like use this guy, this pair, ET1, ED1, as a key. And we are going to search it in the second data structure, the one on your right? Say we found it. So we found this entry, and we have this value ET1, D1. That basically means is, if I add this encrypted time T1 and encrypted offset D1, the time encryption would be ET1 and D1. Now, what I would use that as the key to look for the left data structure, and we'll get the position 13. That means it's like in the sorted array, it's in position 13. I do the same for ET2 and ED2 and get the position 57. Now that the 13 is less than equal to 57, I can safely say that my response to this query is true. Any questions? This can be a little tricky. So the tricky part is the first part, is the data structure on the left. It basically keeps a mapping of, so think of the array positions as you take all the times, encrypted times in your data structure, you decrypt them, right? You put in an array and you sort them, right? Now replace each plain text value with this encryption. Then the mapping you'll get that is basically this ET1 and 7, right? That's basically it. Okay, because like this is the plain text, underlying plain text order. It's not the encrypted times order. And the second part is basically saying, if I were to add ET1 plus ED1, what would be the result? So rather than, because my encryption scheme does not allow me to add, so I have to explicitly give it to you. That's basically this other table, the one on the right. So once you have that, you just like figure out this order in the sorted array. If the first one is smaller, then you know that it's good. I mean, the result is true, response is true. So which is the case in our case, because 13 is less than equal to 57. Okay. Now what we have seen so far is basically how would we encrypt the audit log to do join, and how would we check time comparison. If I take 2 times, how would I compare them? So now we are ready to actually look at how the compliance checking works. I'm not going to go into too much details. I'm just going to like gloss over it a little bit and show an example. So what we have seen so far, right? So the hospital, the audit log is in the cloud. Our algorithm is going to run in the cloud, right? So hospital would time to time add new events to the log, like in bulk, like say it will gather 7 days of log, encrypt them, and ship it to the cloud, right? And when it comes time to audit, what we are gonna, what the hospital is gonna do is give a constant encrypted policy, some tokens. The tokens we talked about for taking joins, that's the token, right? And the algorithm would get also the audit log, which is the encrypted, and it's gonna tell you either there is a violation or there is no violation. Okay. Yeah, so it will give you the auditing result. So our auditing algorithm's main function name is called ereduce. So it takes 4 arguments. The first is the encrypted audit log, because that's the compliance you're checking, and the constant encrypted policy. So the tokens, because those are the ones you need for taking the join, and a substitution. So substitutions are basically, you can think of them as maps. It's a map of variables to their values. So I'll tell you, this will become more clear in a couple of slides, okay? And it returns either true or false. It returns true if the log satisfies the policy, or it returns false when the log does not satisfy the policy. That's basically what it does. Questions? Okay. So formal specification, not difficult. I'm gonna run it through. It's very easy. So if your policy, it's basically says the true. What would be the result? It's a true, right? Right. And the thing is, if it's a predicate or a table name, what you want to do is first get concrete values for the column names, and check whether it's in the log. Basically, what you want to check, what it does is, remember one of the examples we checked whether Bob is a doctor? That's basically what is happening here. It's written a little weirdly, but that's basically what it's trying to say. The next one says, if you have a conjunction of 2 policies, what we are going to do is check the first one, and then check the second one. If both of them are true, then we'll return true. So I don't know whether you can see that. Can you see that mouse pointer in the screen? So that's basically an AND, right? So it's basically saying phi 1 is a policy, phi 2 is a policy, and this is an AND of a policy. So what you do basically is recursively check the first policy and recursively check the second policy. If both of them are true, then you satisfy that, yeah, it's true. Else you say false. The most interesting part is this guy. So this guy basically says, for all x that satisfies G, it also satisfies phi, right? So the first step is basically what you do is find out what satisfies G, all substitutions for x that satisfies G, right? And you basically plug it into the phi and see whether phi is satisfied, okay? So now let's look at an example. So we're gonna start off with very simple example. So it basically says every individual accessing the sensitive patient information is in the role of a doctor. So this is the represented policy in the logic. It basically says for all principles P and all times T, if principle P does a sensitive action at time T, implies that P is a doctor. That's basically what the policy says. Say we have this log, right? So the sensitive access table and the role table. For ease of exposition, I'm just showing here the plain text value, because if I show the encrypted value, it would make no sense here. So, but believe me when I say this, these are encrypted. When they're handled by the algorithm, these are encrypted, each of the values. So this basically means that the employee J1 does a sensitive access at August 2007, and employee is a doctor. Okay, so so the first thing what it does is it checks, and remember this, each of them are encrypted with a separate key. So each column is encrypted with a separate key. So it's K1, so let's say it's K1, K2, K3, K4. Okay, so the first thing we are going to do is figure out who has done sensitive access. So that's basically what you have to figure out. So in our case, there are two guys, J1 and B1, and they accessed one on August 2007, another one September 2007. So that would be our substitution. So it basically says for P, for when P is J1 and the time is August 2007, there is a sensitive access. That's basically a variable. It's the whole thing is a substitution. Okay. The next one basically says there is another substitution. Basically says, by the way, B1 did access to at August 2007. So now what you have to check is that both J1 and B1 are doctors. So basically, what we have to say is whether this thing actually appears in the roll table, right? E means encryption, K is the key, right? Now, here is the interesting part. Remember how we said that the employee column in the roll table is encrypted with K3, but this guy is K2, right? The value we got are K2. How can we search this? So this is where the token comes in. So we can use the token to change this with key K3, right? If we are given that token, we can change it, right? Then we can search whether this entry actually appears in the roll table. Okay. That's basically how the algorithm works in a very simplistic fashion. Okay, so let's say we're going to talk a little bit about the security assurance. So in our security definition, we assume the policies are publicly known because anybody can go up and look up HIPAA or GLBA, right? They can search a little bit online and figure out all these constants, like doctors, institutions, or 30 days. They can figure this out. So we assume that even the adversary knows this. So that's our security definition takes care of this. And additionally, we say that these table names we talked about and their corresponding column names, they are publicly known too. Okay, so they are publicly known. And the only requirement we have is that adversary do not know encryption of a single value. So it should not know what should be the encryption of Omar with K1. So it should not know that value. As long as that value Omar is non-constant, it's not a constant. Okay, constant it's okay to know, but non-constant it should not know. Okay, and our definition is based on a novel form of audit log equivalence. So we have a definition which basically says that these two logs are equivalent in some notion. Let's not worry about that for the time being. Okay, and its security definition is basically an indistinguishability kind of result. It's basically the adversary cannot distinguish between two things. So in our case, it's logs. Say what we have is a log equivalence class. Basically what it means is each log in this class are equivalent. There is in our definition of log equivalence, all of the logs in this equivalence class are equivalent. Now the security definition basically says that if you pick anyone randomly, right, and encrypt it and give it to the adversary, and he can run any polynomial time algorithm, he cannot tell which one of the log I gave him. He can just figure out like, oh, this is one of the logs from this equivalent class. So what makes this more interesting is for any plain text log, for any arbitrary plain text log, the number of elements in the equivalence class is infinity. So this size is infinity. So that's so the thing is like he can just say that this is one of the infinite things. Doesn't know which one with like significant probability. So these are all probabilistic results. These are not absolute results. So with high probability, he cannot computationally differentiate between these things. Okay. So now that we have finished talking about the security assurance, let's talk a little bit about the implementation. So we actually converted majority of HIPAA and GLBA in our language. right? So we converted them in our language. The logic you saw, the scary one. And we implemented two algorithms. One for that works with logs encrypted with Enumia det. The other one encrypted with Enumia KH, the keyed hash version. So we implemented both of them with C++. And tested with synthetically generated traces. We stored them in SQLite databases. So synthetic database is the reason behind it. The reason behind it is like no hospital would give us the log because they contain personal information, right? And the other thing I think, so I'm not absolutely sure about this. If I actually end up during the evaluation catching a violation, I think I'm bound by law to report it. So they don't want to get into this legal mess. So it's very ambivalent about sharing this kind of audit log. So I have to test with synthetic audit logs. So our baseline is the algorithm that works with plain text. So no encryption, right? That's our baseline. And these are the computational overhead. It basically says for Enumia det, we have 3 to 9% of overhead. This is time overhead, not space. And for Enumia KH, we have 63 to 406%. So 406 is not a mistake. It's the actual. It takes four times longer. The reason it takes 4 times longer is due to this. We do this key changing operation. Like using the token, we change the hashed keys. That's what the cost is incurred, right? Now let's see the HIPAA results. So the x-axis is number of privacy-sensitive events in the audit log, right? And the y-axis is the average execution time in milliseconds to check one privacy-sensitive event. Okay. So as you can see, if the log grows, the time grows, average time. And the maroon one is the execution time of the plain text algorithm, right? And the blue one is the deterministic portion. So if you see in the whole thing, they are very close together. So that actually means very low overhead. And the black one is the KH one, which is more secure, but as you can see, they have a very high overhead. If you see so this is the Graham-Leach-Blaley Act. They have the similar trends. So the plain and the deterministic one are very close together, but the keyed hash approach has a humongous overhead. So like whatever you want to, so whatever fits your application, you choose that. If you want more security, choose KH. If you want more efficiency, look for the deterministic encryption. To summarize, so what we did was presented 2 simple audit log encryption schemes and enhanced an existing auditing algorithm to handle encrypted audit logs. Talked a little bit about the security definition, and finally empirically evaluated that our approach is actually efficiently usable in practice. Okay. So thank you for your attention. I'll take any questions you might have. No questions? Yes.
So what's your storage overhead?
So do I have to push this guy?
No, you don't.
Okay. So for the KH, it's like around 4 times. 4 times more space, a little bit over 4 times. On the deterministic encryption, it's twice almost. So that's basically the space overhead we have. Any other questions?
So the setting is you assume the data owner send the program to the cloud to execute?
Yes. So the auditing algorithm also runs on the cloud. So it's because other than that, you have to have this communication overhead. So that's basically the setting is. Any other questions? Okay. Okay. Cool.
Thank you, Stephen.